So today we will continue our discussion of virtual memory that we started last time. The two main concepts today are going to be page faults and page replacement. So these are going to be the two main concepts in today's lecture. Now let's try to remember the main concept behind virtual memory. So what's the main concept behind virtual memory? What's that? Well, locality is not the concept behind it. That locality is why virtual memory works, why it works, and why it doesn't slow the system down. Why virtual memory doesn't slow the system down. So I
think it's the idea that for any given process, you're only actually using a subset of its entire code, and so
the code and the data, code and data. You are only using a subset of the memory, the address space of a process. So that subset that you are, or that the program is currently using, is what you need to have in physical memory. The rest of the code and data can stay on disk because it may never get used. Like now when I'm running PowerPoint, I've been using PowerPoint to display these slides. There are many, many features of PowerPoint that I never used in the lecture. So there's no need to load them in physical memory unless they are needed. Now, the last concept in today's lecture, in last lecture, was page fault. The concept of a page fault. What's a page fault? So the last thing that we talked about last time was a page fault. And what's that? So here in this...
When you're trying to access memory that's not in your virtual memory, but it's in the physical memory.
Well, it's the other way around. So when you are trying to, virtual memory, everything is in virtual memory. Virtual memory is not a real thing. Virtual memory is, or what we also call logical memory, is all the pages that constitute a program's address space. So in this case, logical memory is 8 pages. And these 8 pages, where are they physically? All of them are on disk. So all 8 pages are on disk, but only 3 of them are in physical memory. And the page table indicates or gives us the mapping between virtual and physical. So it says page 0 is in frame 4, and it's a V, it's valid, it's in physical memory. So page 0 is in frame 4. Page 1 is an I, it's invalid, it's not in physical memory. So I don't have a frame number for it because it's not in physical memory. So that's what the page table tells us. Okay, so a page fault is trying to reference a page like page 1 that is not in physical memory. And we will see today how the system handles this. We will see the details of handling a page fault. But obviously, what's the most obvious thing that the operating system will have to do in this case?
Go to disk. Go to disk and load.
Yeah, exactly. Load it from disk. Go to the disk and load it. But as we will see, there are lots of details. Okay, so that's what a page fault is. So we will need to, the system will have to fetch the missing page that is not in physical memory, fetch it from disk to physical memory, and then update the page table to indicate this. And this picture shows it very well. So this program has a load instruction, a memory instruction that's trying to load from address M, and this address M is in a page that is not in physical memory. So there is an I for that corresponding page table entry, indicating that this page is not in physical memory. So this will result in a page fault. So the page fault requires hardware support. So we need hardware support. The hardware, when a page fault happens, when a program references a page that is not in physical memory, or it references a page with an I, or with an invalid bit, the system, the hardware will give control to the operating system. So now this is just like an interrupt. It's an interrupt. It's one of the interrupts. And the system, the operating system, has an interrupt handler for the different kinds of interrupts that may occur. So it's just going to handle this interrupt. It will invoke the corresponding interrupt service routine. And what will that interrupt service routine do? First of all, it will check if that reference is to a legal page or not. Because the program may have 100 pages, and it's referencing page 701. There is no page 701 for that program, so that's an invalid access, which may probably result from an uninitialized pointer or something. Uninitialized pointer that has junk in it, and it's referencing a page that doesn't exist. So in this case, the system will just terminate the process. It will not proceed any further. But if it's valid, if it's between 0 and 99, that's a valid page number, then the system will fetch it from disk. And it will find it on disk, and it will load it into physical memory. Now, assuming that there is a free frame for it. Assuming that there is a free frame. Now, if there is no free frame, if all the frames are used, what do you think the system should do?
Drop one of the frames to make available space.
Yeah, exactly. So it should victimize one of these frames. And later in this lecture, we will look into different algorithms or policies for doing this page replacement. So we need to do a replacement. If there is a free frame, we'll just use it. If there is no free frame, we'll have to pick one of these frames that are used, and according to one of the policies that we will be studying later, this lecture, and victimize it, meaning we will copy it to disk. By the way, do we always need to copy that to the disk? The page that we are replacing, or the frame that we are replacing, do we always need to copy it to the disk? Yes or no? Why and why? Well, the answer is no.
Yes. Why?
So we don't always have to copy it. Why? Yes?
If it hasn't been changed.
Yeah, exactly. If this page has not been changed since it got loaded, there is no need to copy it back to the disk. If the program loaded this page and it only read from it, it never wrote to it. So it was accessed only in read-only mode, only reading, no writing. Then this page did not get modified, and there is no point in copying this to the disk because the copy on the disk will match the copy in physical memory. So this will be a waste of time, and as we will see later, disk access is extremely slow. Now, how will the system know? There is a bit that we'll talk about later. There is a dirty bit that is associated with each frame indicating whether it got modified since it got loaded or not. So there is a bit indicating whether that page got modified or not. If it got modified, we need to copy it back to the disk. If it did not get modified, there's no need in copying that to the disk. And all what we need to do is copying this, the new page, copying the new page into this frame in physical memory. And then after the system does this copying or loading of a page, it needs to update the page table. So now this I must be changed to a V. So it will be, or in a real system, it's a 0 or 1. A bit is a 0 or a 1. There is no I in V. So it must be changed from 0 to 1, or from 1 to 0, whatever encoding the system is using. So we need to change this bit to update this entry in the page table to indicate that this page is now in physical memory. Then the operating system will need to restart the instruction. It will need to restart the instruction that got interrupted. So this load instruction, it started but it never finished. So the system will need to restart it now after the page got loaded, and restarting requires hardware support. So the hardware must support restarting an instruction. So if an instruction got interrupted, nothing will get committed until we restart the instruction. Then everything that all the modifications that this instruction makes will get committed. Okay, so we need hardware support for restarting an instruction in order for this to work properly. We talked about demand paging last time. What do we mean by demand paging?
You only load a page if it's been requested.
Yeah, we in general, loading pages based on demand or request. Now, strict demand paging or pure demand paging means that we never load any page that did not get referenced by a program. Only if a page gets referenced by a program, we load it. That's pure demand paging. But as we will see later, when we look into operating system examples, we will see that real operating systems do not implement pure demand paging. They implement demand paging, but not very strictly. So if when a system loads a page, a system will typically load some of the adjacent pages. And what's the point in loading a couple of adjacent pages when you load a page from disk? Locality, yeah, because it means locality, capitalizing on the locality of reference property of programs, or locality of reference principle, that programs, if a program references this location, it's likely to reference adjacent, spatially adjacent locations in the future. That's spatial locality. And temporal locality, if a program references memory location X now, it's likely to reference X again in the near future. So that's temporal. Temporal is adjacency in time. If I'm referencing X now, I'm likely to reference X again in the near future. And spatial locality is adjacency in space, which means that if this reference is to location X, the next reference is likely to be to location X plus delta, where delta is a small number. One of the adjacent or neighbor memory locations. So two different concepts, temporal and spatial. And these locality of reference program characteristics, these are the reason why virtual memory works. These will minimize the number of page faults that will take. Another thing, besides temporal and spatial locality, keep in mind that a page is not just one data element or one instruction of code, right? A page, if you have a 4 kilobyte page and you are doing 32-bit integers or 4-byte integers, that's 1,000 integers. Or if it's 4 kilobyte of code and each instruction is 4 bytes, then that's 1,000 instructions. So a page is not just one piece of data or one instruction of code. It's thousands of integers or thousands of instructions, which means that if you fetch a page, if you load a page, and because your access to the first integer in an array resulted in a page fault, then referencing element number 0 in that array will result in a page fault, but referencing elements 1, 2 through 999 will not result in a page fault. If a program is sequentially processing an array and referencing element number 0 results in a page fault, now you will bring the whole page. Then referencing elements 1, 2 through 999 will not result in a page fault. So that's why page faults do not occur very frequently in a program. Otherwise, page fault handling would kill the performance.
You just use an array as an example, but how would that differ from a list? Because with an array, we expect contiguous.
Yeah, definitely. A list has, a list has much worse locality. So it's not. A list can be, in the worst case, scattered all over memory, and a list may fall in many different pages. So that's why the performance of a list is much worse than the performance of an array. An array has much better, caching performance, and is likely to result in much fewer page faults than a list. Yeah. So it's unless you do something to improve the locality of reference for your list. For example, in creating a list, you don't invoke the system memory allocator by calling new for every list element, but you can allocate a pool of elements, like a block of elements, and reuse them, and bring 100 elements, for example, and reuse them, so that the elements in a list are more adjacent in memory. So that will improve the locality. So there are things that you can do to improve the locality of reference to a list. Okay, but in general, if you do a separate memory allocation, you invoke the system, you make a system call and ask the system to give you the next memory location for every list element. In the worst case, each element could be in a different place in memory, and you'll have poor caching performance and more page faults. Okay. All right, so now we will look into the details of page fault handling. So this slide is probably the most dense slide that we have seen so far. Why? Because it has all the details of page faults. And in fact, most of this stuff is not new to us. Most of it is are concepts that we have seen, and that's why this is an interesting slide, because it will allow us to review many of the important operating system concepts that we have studied in this class. So these are the different steps that the system will be taking in order to handle a page fault. So now, the hardware trapped to the operating system gave control to the operating system because the program referenced a page that is not in physical memory. What will the system do? What will the kernel do? The very first thing that the kernel will do is saving the state of this process that resulted in the page fault. So we'll have to save the state, save the registers. And why is this important? Why is it important to do this at the very beginning? To save the values of the registers of the process that got interrupted. Why? Yes?
I think the kernel's going to give another process, the CPU.
Before it gives it to another process, the kernel itself is a program. And the kernel is a program that will be using the CPU, and it will be using the CPU registers. So the kernel itself will be modifying the values of the registers. So before the kernel does that, it will save. The very first thing that it will do is saving the state of the registers before the kernel starts modifying these registers. Because keep in mind that the kernel itself is a program that needs the CPU in order to run, and that will be modifying these registers while it's running. So that's what the kernel will do in the beginning. Then it will determine what kind of interrupt is this. A page fault is just one of many interrupts that the system handles and that drive the system, as we have seen. We have seen different kinds of interrupts in this course. Interrupts from I/O, exceptions, timed interrupts, other kinds of system calls, etc. So it will invoke the the routine that handles page faults after recognizing that this interrupt is a page fault. Now, that routine that handles page faults, what will it do? First, it will check if this reference to this page, if it's valid or invalid, if it's within the valid range for that program. If that program has 100 pages and we are referencing page 7,000, so that's out of bound, that's illegal, and the operating system in this case will just terminate that process because it's performing an invalid memory access operation, and it will terminate that process before, and it will not do any of the subsequent steps. Now, if the access is valid, but the page is just not in physical memory, the system will load it into physical memory. To load it into physical memory, that's a disk copy. So the disk is treated as an I/O device. So the kernel is going to send an I/O request to the disk, to that I/O device, to copy from a specific location on disk to a specific location in memory. So it will send that copy request to the disk. Now the disk is an I/O device with a queue. So that request may not get serviced immediately because there may be other I/O requests, other requests for that device. So that request will be queued, and eventually it will get serviced. When it gets serviced, there are two components of the copying process. First, the disk will have to search for the requested location. So it will have to do a seek, and this is something that we will be learning more about when we get to disk management. And that seek, if we're talking about a magnetic disk, it's seeking means the head of the disk will have to move. And that motion is a mechanical motion. And mechanical means slow. A mechanical system is much slower than an electronic system. As we will see in the next slides, the disk copying from disk will take milliseconds. Milliseconds on a processor with a 1 gigahertz clock speed. 1 gigahertz, that's 1 nanosecond per cycle. So a cycle is a nanosecond. So when we talk about milliseconds, we're talking about millions of cycles. Okay, so millions of cycles. That's because of the slowness of the mechanical system, which is the disk, compared to the electronic system, which is the CPU. Okay. Then we begin the transfer, and again the transfer is slow because we are transferring from that mechanical device into an electronic device. Now, while doing this, we said that this is going to take milliseconds. Milliseconds means millions of cycles. Now, millions of cycles, that's going to be lots of time quanta. And the system is not going to waste these time. It's going to give these time quanta to other processes. So it will send the request to the I/O, as we have learned at the beginning. With an I/O request, the I/O request gets sent to the I/O device, and then while the I/O device is taking care of that, the system is going to find another process that is ready for the CPU. So it will invoke the scheduler, and it will find another process that is ready to execute on the CPU, and it will give it the CPU. And because we're talking about millions of cycles, multiple processes are likely to get CPU cycles, while one process is waiting for the disk to complete the copy. Okay? And eventually the disk will complete the copy. And how will it notify the system?
Interrupt.
Via an interrupt. So it's an I/O interrupt that will notify the system that I have completed processing this request. So now the system will handle that interrupt. It's an I/O interrupt. How will it handle that? Well, again, when the system first gets the CPU, it will save the registers for the process that is currently running on the CPU. So that's a different process than the process that lost the CPU because it ran into a page fault. So it will save these registers before it starts executing. And then what will the operating system do? Again, this is an interrupt. The operating system will have to recognize that interrupt, to identify it, what kind of interrupt this is. Each interrupt has a number. And it will identify it as an I/O completion interrupt. And handling this for a page fault will require updating the page table to indicate that the requested page is now in physical memory and the corresponding bit now must be set. Okay? And then, after this is complete, the system will not necessarily give the CPU back to the process that ran into the page fault. Because who gets the CPU? That's a decision that the scheduler makes based on the scheduling algorithm. And now we have seen the different scheduling algorithms, and we know that there is the notion of a priority, right? So this process that ran into a page fault may not have been a high priority process. So the scheduler will decide, which process gets the CPU next, and eventually the process that ran into a page fault will get selected by the scheduler to get the CPU, and when that happens, the system will restore the values of the registers, those registers that got saved here in step 2. So this is what we saved in step 2. We will restore them in step 12, and the system will give the CPU to the process that ran into a page fault. It's a long process. Yeah.
So in the device seek, does that happen when that process has the I/O, or does that happen somewhere in the wait queue of the I/O?
I'm not sure I understand the question.
So you mentioned that for step 2, under number 5, that you would have to find wherever on the disk that piece of code or whatever it was. And what I want to know is that seeking process taking place when the I/O has been granted to the process? Or does that happen somewhere?
Seeking is the job of the disk. So the disk does the seek. So the operating system sends, an address on the disk. So the operating system basically sends a disk address, and we will see, the details of a disk address. And when we get to disk management, it will send a disk address. That's the source, and a memory address. That's the destination. So it's telling the disk, copy from this disk address to this memory address. So it will just tell it to do this. Now, the copying will be done by the disk. So in order to do that, the disk will have to seek to find that address by moving the head, because the head of the disk may not be at that location at this point. It may be at a different location. So it will have to move the head, which is the interface between the system and the disk. It will have to move the head to reach that target address, and then it will start transferring data from that address to the memory address.
So this starts happening while that process still has the CPU?
No, of course not. So once the process lost the CPU in step 2. After step 2, the process does not have the CPU. So from step 2, at step 2, the kernel has the CPU. And in step 5, the kernel will send the request to the disk. And now this will be done in parallel with 6. As we have seen in the earlier lectures, right? Remember the overlapping between CPU and I/O? So now this is I/O, that the system sent a request for I/O. Then the system will invoke the scheduler to find another process to get the CPU. So while the disk is doing this, several processes may get time quanta and execute on the CPU. Now, what's the state of the process that ran into the page fault at this while this is happening? Waiting. It's just waiting. Cannot do anything. It's just waiting for the I/O device to complete this. Okay. Now, this is obviously a long process. You know, the good thing about this is that it reviews many of the concepts that we have learned in this course. Now, among these steps, which step do you think is the most time consuming? Yeah, step 5, where you access the device. This is because there is a mechanical system involved that's extremely slow. Okay? So this is the slowest, the most time consuming step. And again, you know, page faults do not happen very frequently. If they happen frequently, obviously this is going to kill the performance. But they don't happen frequently because of the locality of reference. And that's why, you know, this doesn't happen very often. If this happens with every memory access, then, you know, you will be feeling that. You will be feeling the, you know, that slowness. Every program will feel very slow if this happens with every memory access, spending milliseconds just to access one memory location. That's a huge amount of time. Milliseconds is millions of machine cycles. Okay. Now, the effective access time with page faults. So with page faults, our effective access time is just the weighted sum of the access time with no page fault and the access time with a page fault. So P is the probability of a page fault, or the page fault rate, multiplied by the time when there is page fault, and 1 minus P is multiplied by the time when there is no page fault. Let's look into actual numbers. So let's assume that memory access time is 200 nanoseconds. So again, 200 nanoseconds, that's hundreds of CPU cycles. So memory access, main memory is hundreds of CPU cycles. Disk access, or the page fault, because, you know, the page fault handling is dominated by disk access. As we said, disk access is the slowest step in those 12 steps that we saw on the previous slide. So that's 8 milliseconds, millions of cycles. So what's the effective access time? It's just the weighted sum. If the page fault rate is 0.001, which means 1 out of 1,000 accesses will result in a page fault, and this is very realistic, you know, like, you know, thinking in this, you know, here's a sequential access to an array, and if each page has 1,000 elements in it, then this will result in a page fault, and the remaining 999 will not result in a page fault. So 0.001 multiplied by the time for handling a page fault, which is 8 million nanoseconds, and the time with memory is 200 nanoseconds multiplied by 0.99. That will give you an effective access time of 8.2 microseconds, or 8,200 nanoseconds. Okay, so basically it's a weighted average of something in the hundreds and something in the millions. So the effective access time is in the thousands, which is microseconds. Thousands of nanoseconds, which is microseconds. 8.2, so that's a slowdown of 40. Where does the 40 come from here?
It's 200 times 40, 82.
What's that?
200 times 40 is 8,000.
Yeah, so exactly. So this is the access time with page faults. The access time with 0 page faults is just the memory access time, which is 200. If we have no page faults, the access time will be memory access time, which is 200. So it's 40 times slower on average. Now, 40 times slower is like an order of magnitude slower, which is not too bad. Right? It's still microseconds. Microseconds, 8 microseconds, and you know, for humans, you know, we don't feel microseconds, and we don't even feel milliseconds. We feel seconds, or at least a big fraction of a second. We may feel a big fraction of a second, but we don't feel microseconds and milliseconds. Okay, now if we want the performance degradation to be less, to be 10%, like we want the effective to be 220, so we just set up the equation and we solve for P. So we just say we want this to be 220, and that's 200 multiplied by 1 minus P, plus P multiplied by 8 million, times 8 million. And you solve for P. And in this case, you get a smaller P, which is 0.00025. That's not unrealistic, by the way, because of the locality of reference. Getting a low page fault rate is not unrealistic because of the locality of reference.